So this is the what about your conduction angle? Conduction angle gamma d. Conduction angle will be 2 pi because the diode conducts completely from 0 to 2 pi. So your conduction angle is 2 pi. Okay. This is this is L load. Let us discuss one more load, that is your again a single phase rectifier, uncontrolled rectifier, but this time we are going to use RL load. So what happens with the RL load part? So Vs is again Vm sin omega t. Again we have to take out the waveform of V naught, and this is Vd, and this is my current I naught. Okay, so we'll first write down the what happens when your current, when your diode is in the positive half cycle. Your this is positive, this is negative. The forward when the diode is in forward bias condition, D is on, right? When D is on, so you will have, suppose this is my D is on. Okay, so D is on, current is conducting. So if you write down the equation, you will be able to write down that Vm sine omega t is equal to the current equation. You can write I naught omega t into R. Okay, because this omega t will I naught will be the function of R, omega t, plus L d I of omega t upon dt, the voltage across L. This is L and this is R. So this is the equation, and if you know this equation, it is similar to linear differential equation. Okay, linear differential equation, where you have the term dy by dx is equal to py, sorry, dy by dx plus py equal to q. So you will have an integrating factor. So you can replace this like dl. If you replace this like this, di of omega t by dt plus r by l I of omega t equal to Vm by omega L or Vm by L sine omega t. So this equation is similar to this, and if you solve this equation, so you will be able to get an integrating factor. You will be able to get the equation in the form of y of integrating factor is equal to integration q into integrating factor d omega d d of t plus c. You can solve this equation. Overall, I'll not go into the mathematics part, but I will go into the your how you can analyze the waveform, because this waveform contains two terms, R and L. Okay, so you might have seen this type of thing in your load in the fault calculation also. In the fault calculation, symmetrical fault calculation, there you have seen RL load and there you have seen Vm sin omega t. The same equation would be there also. So it will contain one, it will contain, you can say that the AC component, and it will contain a DC component. Okay, so if you have, so if you write down the omega t part, So you can write Vm. The AC component will be root under R square plus omega L square. This is the current, and AC component will be sine omega t minus phi, where phi is tan inverse load power factor angle, you can say that, omega L by R. So this is my AC component, and it will have some DC component also, that is your K e to the power minus R by L into T. So this is my DC component. Now, similarly, put this at omega t equal to 0, the current is 0. At omega t equal to 0, the current is 0. Okay, so put the values at omega t. So you can get 0 is equal to Vm by omega L. So Vm by root under R square plus omega L square. Sin omega t will be sine minus phi, right? And here if you put the value t, so you can say that it is t equal to t equal to 0, because omega will never be equal to 0, because omega is 2 pi f, right? So frequency is not equal to t is actually 0, so the multiplication is 0. So if you can put here, so you will be getting k. So k is equal to actually Vm upon sine. From here you can find out k is equal to Vm upon root under R square plus omega L square sine phi. So this is your equation of K. So overall equation, if you write on I naught omega t is equal to Vm by root under R square plus omega L square sine omega t minus phi plus Vm by root under R square plus omega L square sine phi e to the power minus R by L into T. So this is the overall equation which you are going to get. And here, this is my AC component. This is my AC component and this is my DC component. And this is a constant component. So the waveform which you are going to get will be having both the components. Basically, this is my sinusoidal component and this is my exponential component. Okay, this is my exponential component. So the waveform which you are going to get will be having both the component in your current waveform. Okay, so let us draw the waveforms. So this is my sinusoidal waveform, and so basically if you have seen the current equation, it has a sinusoidal waveform as well as it has a exponential waveform. So if you draw the circuit during when the diode is on, so what happens is that this is my v voltage across your resistance, that is VR, right? VR, and this is my VL. So the drop will be there in VR and there will be a drop in VL, right? So there will be two types of two kinds of like if you draw if you VL is equal to, what I can write about VL? VL is equal to Vs minus Vr. Okay, so VL, you can write di of omega t by dt is equal to Vs minus Vr. So just you have to replace like this L. Now this di of omega t is Vs minus Vr by L. Okay. Now what happens if your before when your Vs is greater than Vr, when your Vs is greater than, first of all we will draw Vr. So how you can draw the Vr characteristic? So this is the Vr. This is Vr. Okay. Now why I'm drawing this type shape? Why I'm drawing Vr in this shape? So because Vr is I of omega t into R, right? And I of omega t is having a sinusoidal component as well as exponential component. R is just a constant. So if you can see the difference of the shape, this is pure sinusoidal, but there in this waveform there is exponential form. That's why the peak value is different. Here the peak value comes here for a pure sinusoidal, but the peak value comes here for this. Now so here if you find out that there are two regions, till this region, till this region Vs is greater than Vr, Vs is greater than Vr, right? So this is my Vs. Yeah, Vs is greater than Vr. So the current is in rate of change of current will be increasing. Okay, that means I naught increases. But after the waveform, after this point, if you see, after this point, this the current is Vr is greater. So you can write after this point I naught decreases. After this point the rate of change of I naught decreases. Okay, so this is the nature, that what happens, there is a shift in the waveform, therefore your conduction starts from 0 but ends at beta. So if you draw the waveform of I naught, you will get, this is my I naught. So you will get a peak value, you will get a peak value at this point. So you will get like this. The peak has a difference, right? And you, the waveform will get zero here. Okay, so this is how you can draw the characteristics. The peak value occurs here. Okay, and here the rate of is getting constant. Okay, so the conduction start from 0 to beta, and this is for I of omega t. What about V of omega t? Again, V of omega t will be similar to your diode, but the conduction, because the current has delayed the conduction, the current will be flowing till here. If you see from pi to beta, there will be a there will be current flowing. Okay, Current has started from 0 to pi, no doubt, because the diode is forward bias, that's why the current is flowing. But from pi to beta, because the current is not equal to 0, it will tell your diode to remain on till the current get to 0. I am again repeating it. From 0 to pi, the diode is forward bias, diode is conducting, diode is conducting the current to the inductor, inductor stores energy, inductor remains there. But uh, because of the delay in the current peak, current has not reached to 0. It has to get to reach to 0. That's why it forces the diode to remain on and to conduct from pi to beta. Okay, so that's why if you draw the waveform for your I naught V naught, you will get like this. So this is the whole cycle. So it will start from alpha. You will get a pure sinusoidal waveform. You will get a pure sinusoidal waveform till pi, but there is some negative portion also comes in picture because of this, because of the current, because of the delayed amount of current. Okay, so that's why if you uh, uh, if you can. And what about your diode characteristics? So diode VD remains on for a specified period, but from here VD will experience a voltage like this, because VD is equal to Vs minus V, or sorry, VR naught minus V naught, right? So during this portion V naught is negative, because V naught gets negative from here only. So the remaining waveform will come in picture. So minus Vm, you can say that this minus Vm sine beta, because at omega t equal to beta appears, starts from here, and your V naught voltage is 0. So this voltage is Vm minus Vm sine beta. Okay, so this is the waveform which you are going to get. Now talking about let us talk about your values, RMS values, average values. So if you see the voltage waveform here, voltage V naught average value 1 upon 2 pi integration 0 to beta. So there is one change, because now the conduction is from 0 to beta. Vm sine omega t d omega t. So integrate it. So Vm upon 2 pi sine omega t will be cos omega t minus cos, so you will get 1 minus cos beta. So this is my average value of the waveform. Okay, so and what about the conduction period, gamma d? Conduction period is from 0 to beta, so beta cycle, you can say that, and beta will be always greater than pi, always greater than pi. So beta angle is always greater than pi. Okay, so overall, we can conclude ourselves with this topic, single phase half wave rectifier, uncontrolled rectifier, and basically you must be able to focus on the types of loads and the types of waveform with respect to those loads. So if you are able to understand how an inductor influence the waveform, you will be get to know that there will be some terminology that continuous waveform and uh, continuous and non-continuous, discontinuous, continuous and discontinuous. So if your current goes does not touches zero, it is called as continuous, and if your current touches zero, it will be zero, it will be called discontinuous. Okay, so it depends on the inductor value which you are putting. Now suppose here you are getting a beta here. Okay, if the inductor is quite large, means the energy stored in the inductor is quite large, so you will get a waveform like this. If it is again more larger enough, so you will get, it will never touch the zero cycle. Okay, so this type of waveform is because of the inductor's capacity or to store energy. So if large inductor is there, it will never make the current to zero, and that will make your output voltage still to conduct regularly. Okay, so this is the nature of your waveform with respect to your inductance. Okay, actually overall the problems comes with the inductance. So, I hope this is a clear picture. Now, in the next lecture, we won't derive everything. I'll just show you the diagram. I will show you the output waveform. We'll change our focus to some other parameters, how we can calculate the power factor, how we can calculate the distortion factor. Overall, this is the basics, and you must have must be able to redraw it in your notebook it by yourself. Okay,